Cool. Hello, everyone. So today I'm going to talk about how reproducibility and productivity are inextricably linked. And that might seem like quite an abstract concept, but specifically I'm going to start by comparing where data science, machine learning, and AI is today versus where software development and DevOps is. So who in the room considers themselves to know a thing or two about DevOps? Okay, cool. And who considers themselves sort of a pure data scientist, statistician, and so on? Okay. Anyone think that they do both? Good. So I think there are some really interesting parallels between these two worlds. Myself and my team have been doing some research in the last 6 months into data science teams and software teams, and looking at sort of where data science is compared to where DevOps is. So I'll talk about that in a minute, and I'll pull out some facts about what we've learned from those conversations. But first, I want to start by just talking about where software development was in the past. So in the 90s, software development was a bit of a mess. It was actually quite painful to do software development. Work was generally split into silos. There was a development team, and then there was a separate testing team, and there was a separate operations team, and there was little sort of coordination around how code and production artifacts flowed around between these different groups. And this caused a huge amount of pain. So, for example, in the 90s, doing software development, some people didn't have version control. It's almost impossible to imagine not having version control as a software developer in 2018. But let's think about what it was like for a second. So without version control, you were emailing around zip files of your source code, or maybe diffs. And if two people changed the same files, then maybe one person's changes would just get clobbered. So that was pretty painful, and it was obviously problematic, and it slowed people down. So that's the dev side. And then, like I said, there was a separate testing team. And so sort of once, as a developer, you get to the point, as a software developer, once you get to the point of saying it works on my machine, and there's a whole nother conversation around works on my machine, then you would share the version of the source code that you think works with the testing team, either by emailing it to them, or putting it on a USB stick, or putting it in exactly the right place in your shared drive, like your Office file server. And then at some point later, they'd pick it up. So there'd already be like some delay before they get round to testing your version of the code that you're proposing. And then when they test it, they might not have exactly the same environment that you had when you were developing it. So there'll be issues around that. And what's more, just having this high latency between you broke something and you know that you broke something has this impact where you lose this valuable context. So when you've been working on a piece of code, like in the last hour, you remember what you've changed, and you've sort of paged all of that context into your head. But if it's a week or 2 weeks before the testing department gets back to you with the bugs that you've introduced, then you've lost that context. It's just the nature of our minds that we have lossy short-term memory, and then we have to context switch back to it. So that results in a sort of slow and frustrating cycle between development and test. And again, this is sort of software development in the 90s. Operations in the 90s was very much a sort of throw-it-over-the-wall mentality. So there was a separate ops team that looked after the servers, and you email them a WAR file or something, and they upload it onto a Tomcat server. And then inevitably you find out that the developers failed to account for some non-functional requirements. So like the new version of the code is 10 times slower than the old version was, and none of the testing that the testing team did showed that up, and it only shows up in production. And the monitoring is sketchy. You're only monitoring like the memory usage and the CPU on the servers. You don't have insight into what's actually happening in like deep in the software. So you end up with users finding bugs, and then Ops try and fix it, and they can't, and eventually you end up with the developers SSHing into the production box. Who's ever SSH'd into the production box? Yeah, I have. I used to spend a lot of time doing that. I'm not proud of it. So this is like the process gets skipped during an outage because everyone's stressed and everyone's shouting at each other. And then you make some changes that you think will fix the problem, and you actually end up introducing some more bugs. And so I see people nodding. And so like everyone is sad. And basically the upshot of this is that there was this huge pain in the 90s with software development, and there have been some huge steps forwards to fix them. But before I talk about how we fixed them, like how did we actually ship anything when we were in that mode? And the answer is we shipped things slowly. The release cycles were weeks or months. And this is what happens when you have bad tooling and process, or maybe it's not fair to call it bad tooling, but it was tooling that wasn't really fit for the task at hand. It forces organizations to choose between speed and safety. Because you can have people SSHing into the production box and making fast changes, and they go live immediately, but that's not a safe way to do things because you don't have any tracking of what happened, and you're likely to introduce new bugs. And so when there were these slow cycle times, most companies were forced to choose safety. And so software development was slow. And I just want to take a moment to, the word reproducibility is in the talk title, and so I wanted to sort of highlight what I mean by reproducibility in this context. So when you're developing software, it's an iterative process. You try something, you change something, you figure out what happened, you learn from it, and then you try something else. And I underlined figure out what happened because the way that software developers figure out what happened is that they reproduce all the variables, and then they see what changed. So they keep as much as they can fixed, and then see what's different. It's kind of like a binary search. You're narrowing in on what was the thing that caused this bug, or why did the software behave in this certain way in this scenario. And so when there's a lack of tooling that helps people reproduce sort of the environment that the software is operating in, then development grinds to a halt. Now, software development has got a lot better in the last 20 years. We've had the whole DevOps movement, which I'll talk about in a minute. And we're now able to, modern software teams are able to very rapidly ship and iterate on changes to their code and get them into production within minutes in a way that is safe and controlled. And so we've achieved this sort of combination of speed and safety in software development. I want to take a moment just to talk about collaboration as well. So the way that collaboration is done in software development, the way it used to be done versus the way it's done now, like before and after version control, is destructive versus constructive. So destructive collaboration is about just making copies of things. And when you make copies of things and you email them to each other or you send them to each other, however, then suddenly there's no source of truth. There's no like fixed version of that's definitely the version of the code that went into production, or that's definitely the version of the code that Alice was working on last Thursday. And so as soon as you make copies of things, then you get divergence. And then if you have no way of sort of reconciling those divergences, then you end up with chaos. Whereas constructive collaboration is about having a single source of truth, or in a slightly more sophisticated model, sort of a distributed source of truth, like with Git. But in particular, there's the ability to try different things, to have multiple branches, and for diff and merge tools like GitHub to enable reconciliation of changes and keep everyone sane. So version control really enables this constructive collaboration, this constructive mode. And of course, everyone who's sane in software development today uses version control, and it means that developers can collaborate more effectively. It means that the testing teams can see what version of the code they should be testing, which version of the code they can comment on. Of course, things like pull requests help a lot there, where you can propose some changes and then someone else can review them. And even operations are now using version control. My friend Alexis Richardson at Weave talks about this idea called GitOps, which I won't go into in detail, but it's just this idea that you can, that operations, that sort of, there should be a source of truth for what's running in production that itself is version controlled and itself has a complete sort of audit history of all of the things that happened and who made all those changes. And then you can start automating around those APIs. So things are definitely getting better in software development. We have continuous integration. Version control enables CI. So continuous integration is this idea that every time a change is made to the source code, even in a branch or whatever, you can run a set of tests, automated tests that test the software in a bunch of different possible situations that it needs to operate well in. And you can very rapidly get feedback on whether your change broke something that someone else cared about 3 months ago, which you can't really be expected to do manually just by thinking about all the possible cases when you're changing the software. And that fast feedback that you get from a CI system enables us to react to failures when we can still remember what we just did, in minutes, not weeks. And the CI system also has this important role, which is that it's a platform for getting tested, versioned artifacts. So we can say, this version of the code generated this Docker image, which we tested against all the other latest versions of things, and it passed the end-to-end tests. So we now have a relative degree of confidence that we can ship it into production. And once you start getting that confidence that things are okay, then you can start turning on automatic deployment to production. And that's what we call continuous delivery. So continuous delivery is about having this sort of single, traceable way to get a tested change in development into production. What DevOps is really about, the whole DevOps movement in software, is that the ops teams should be able to collaborate in the same way as the dev and test teams do with continuous integration. And one thing that you also need on top of this is good observability and monitoring. So I mentioned earlier that that we previously just had like Nagios alerts when the CPU was too high on the server and things like that. But modern observability and monitoring in DevOps tools with things like Prometheus, they give you application-level observability, application-level metrics. And this allows, and I won't go into detail about that, but what it means is that monitoring now becomes part of the development process. You put the metrics that you care about into the development of the software, and that allows developers who are tasked with figuring out why there's an outage in production to really dive deeply into the specifics of the problem and find root causes. So yeah, DevOps works, and version control enabled reproducibility and collaboration. That unlocked continuous integration. Continuous integration gave us a level of confidence that things were okay, that allowed us to start doing continuous delivery. We've added observability and monitoring, which actually helps developers figure out what problems are when they occur. And now we have both speed and safety in software development. There's this, I've worked on projects which have CI/CD and which don't, and the feeling of working on those projects is radically different. When you're changing code that you don't know, that isn't going to get automatically tested, you always feel like you're going to break something that someone else worked on that you didn't realize or you don't know about. Whereas when you do have CI and CD, you can just relax. Everything is a lot more enjoyable because you know that within 5 minutes of pushing a change, you're going to get some feedback on whether it's passed like 1,000 automated tests. And that's wonderful. It's liberating. So, like I say, we've been talking to dozens and dozens of data science and AI teams. And I'm sorry to say that data science and AI seems to be kind of where software development was in the 90s. And absolutely no disrespect to anyone in the room. I'm sure lots of people are doing it better than the people we talk to. But there definitely seems to be a gap here. And I've got some quotes, which I've anonymized, because I didn't want to offend anyone. But one person said to us, in retrospect, if we'd been able to save the versions or sort of gone back in time to see how some specific data scientist got his learning rates, that would have avoided a lot of questions from the auditors. So we're now seeing the situation where machine learning is getting rolled into more and more important and risky areas because it's showing up. It's being used more and more in big companies for important stuff. And we still see teams not being able to sort of point to a specific change and say who did it or why. There's another one. Someone else said that 2 of the data scientists who worked on a particular model, they've left. They've gone to other companies. And we'd really like to be able to see what they did and how they did it. But actually, it's just gone when they're gone. And this points to the fact that these models are siloed in people's heads. Like, a certain person will be able to remember more or less what they did when they developed a model and how they changed it. But from an organizational perspective, that's very difficult because you can't force everyone to document every single thing they do. I've got a quote about that in a second, actually. Someone else told me a model failed for 3 months and we lost an immeasurable amount of money. As in, we have no idea, we have no way of knowing how much money we lost, but we know it was some. So that's kind of scary. That points to like a lack of monitoring of sort of basic model health in production. Okay, fair enough. I mean, this is all very new stuff and we're still finding our way. Another one was like, after the last audit, I was surprised how many problems in the audit we could have solved by keeping paper logs, right? And it's interesting because scientists like probably still do in many areas, and certainly historically have done, kept very detailed logbooks and notebooks. I mean, this is where the concept of a Jupyter notebook comes from, is the paper notebook, where you wrote down the date and what you were doing and all your inputs and all the things you varied when you're doing science. But if we ask our data scientists we're hiring now to do that, they will leave. And so it seems like there's a lack of tooling around helping make all of this work tracked. And this was one of my favorites. We keep all our data science teams small and in the same room so that they can track their summary statistics by talking to each other and remembering things. I was like, okay, cool. So we have this problem that destructive collaboration is commonplace. I see lots of people emailing and slacking notebooks around. Hands up, anyone who's emailed or slacked a notebook around? Okay, I'm not blaming anyone. This is just because we don't have the right tools yet. It's fair enough. I mean, the tools for managing these things aren't great yet. There isn't much manual documentation, especially in those early stages of developing a model where you're experimenting a lot. You just slow yourself down a lot if you try and write down every single thing you try. And when people are wrangling data, it's often unrecorded, like exactly what they did. Automated testing of models has been fairly rare in the research that we've done. We haven't seen many people with CI systems. Some more advanced teams do have CI systems, and they roll out the models per a specific version in version control automatically through like pushing it up to an S3 bucket and then having that bucket be pulled down into production. But testing is often just done manually by one person, like in a Jupyter Notebook environment that has no tracking. And so we're ending up sort of relying on people to be diligent and write down what they're doing. And also, the deployment is often manual. I've seen a lot of teams where they're just throwing models over the wall. And then they're left in production to rot until someone notices, like the 3 months worth of failed model. And so I haven't seen much model monitoring. This is especially challenging. I mean, there are lots of things about data science that I'll get into that make it a lot harder than software development. It's especially challenging with respect to retraining. So when you see the data's changed and we want to retrain the model so that it's up to date with the most relevant data, I mean, that causes the model to drift with respect to how accurate it was when it was first trained. And we really need to start plugging monitoring into that stuff, into model health, so that we can sort of page people when things go wrong. And I also haven't seen hardly any continuous delivery in the teams that we've spoken to. And that's because there isn't much continuous integration. And you can't do continuous delivery until you're confident that things are working and that there's a good pipeline. So similar to how software development was in the 90s, data science and AI teams are now being forced to choose between speed and safety. Either they're being shipped slowly with meticulous documentation so that you can survive an audit, or they're being shipped unsafely and they're not really tracked, they're not auditable. There's no single source of truth for what's in production and how it got there. And like we saw, we have models that are siloed in people's heads. So the rest of this talk is about how do we get AI out of the 90s. And I hope you can see the color's a little bit dark, but the point I want to make with this diagram is that all of this stuff, all of the benefits that we see in DevOps are enabled by version control. So we've got sort of version control down the bottom here, and all of the steps of the software development lifecycle, development, testing, continuous integration, delivery, sort of deployment to production, continuous delivery, and then once it's in production, how do you monitor it and observe it? In modern DevOps, they are all tied to version control, often Git. So the code is written and developed in version control. Then the CI system tests a specific version of the code, creates an artifact which is tied back to that specific SHA-1 hash in Git. And then when issues crop up in production, what you do is you roll back to a different version that's, again, identified back down to the specific version of the code in version control. And so the mission is how fast can you go around the loop from development to CI to CD to observability and back into development. Yeah, so we can't go around this loop very quickly at all unless we've properly version controlled everything we're doing. So now I'm going to try and answer the question sort of how can you version control AI and machine learning and data science? It's kind of tricky. So like I said, data science and AI has lots more moving parts than you get with software development. So there's version data, there's the environment that the thing was run in, there's the code, but then the code is often put in notebooks, and notebooks are hard to version, and then notebooks, and then the models are also parameterized by lots of variables that, like the learning rate or the batch size and so on. And along with this, a lot of the teams I spoke to said that they needed better metrics tracking. So when you speak to data scientists, the things that they are doing minute by minute are they're looking at the relationship between their parameters and their summary statistics. So like, if I change this parameter, how does it improve, or how does it improve my accuracy, or how does it improve some business metric, like the number of clicks or something? That's not very compatible with the existing tooling, because you'd have to put the metrics in your commits if you were version controlling everything in Git. But it's just not natural to do that, because you're in this fast iterative cycle, and you're in Jupyter, and it's not easy to get to a terminal. So you also need diff and merge for notebooks, data, and code. And at the moment, who's ever tried to do a git diff on a Jupyter notebook? Yeah, it's not pretty, is it? It's kind of hard work because they're big JSON blobs, and the outputs always change, so you get loads of merge conflicts if you try and do anything. And so I think we also need to take inspiration from GitHub here and allow collaborative sort of asynchronous development with forks and pull requests and tracking comments on those pull requests. And if we can solve these things, then it means that we enable creativity and collaboration. We sort of free you up as data scientists to focus on the science with something underneath that's just keeping track of everything as it's changing. And also make everything auditable, so that like our friends in the previous slides can answer sort of how the learning rate was decided on. So that's the first part. Like I say, we need version control as sort of a basic primitive, and without version control, we can't build any of this other nice DevOps stuff for AI. So on top of that, we want to do continuous integration. And so I'm really interested in talking to everyone here. What do you think automated tests should look like for models? Now, with software, it's kind of easy because, in theory, software, like if you put it in exactly the same state and run it again, then it will give you the same result. But models are more probabilistic, like we saw in the last talk. So I think one thing that does make sense to start putting sort of some guide rails around models to test them is to pick some inputs and outputs that you care about that are sort of obviously right or wrong to a human, and put triggers on them and say the test is going to fail if it's more than like 2 standard deviations away from this thing that's obviously right. We're given this specific input. And you should also be testing non-functional requirements with unit and integration tests on the code, if that makes sense too, just to check that the code sort of internally makes sense. And another nice thing about CI is that once you have a CI system and you have an automated test suite, then when someone reports an issue with a model, like something that a customer cared about or something that really mattered to you at a certain point in time, you can make that into a test, and then you can automatically run that test against every future version of the thing to make sure that it's still true. And it forces you to sort of surface all of your assumptions and your requirements. And this gives you faster and more confident development. So yeah, I think it would be really valuable to see more CI in these environments. And then once we've got CI, then hopefully we can start doing continuous delivery of models. And one of the things that's interesting about how this is different to software development is that you want to be able to trigger rebuilding a model either when the code changes or the data changes, because the model is really an artifact of both the code and the data that it was trained on, unlike software. And so you want to be able to say, like, every time there's new data, retrain my model with the last set of parameters and run the tests. And then maybe if they pass, then you do want to automatically deploy to production. And continuous delivery sometimes makes people feel nervous, because you're like, I've turned on this thing that's now just going to automatically like ship every single change that every developer makes on master into production. But there's something that can help with that sort of nervousness, which is to realize that it minimizes the time between breakage and knowing, and that means that you can ship fixes faster, because the people who just broke it are still thinking about what they just did, or they can still remember what they just did. And also to change your philosophy from, you're not trying to minimize the mean time between failure, you're not trying to never break things, you're just trying to be able to fix them really quickly when they do break. And so if you can have a system which allows you to do fast rollback, if something does break in production, then you can get sort of higher number of nines, like 99.999 whatever, uptime with maybe sort of more smaller incidents. And once that becomes part of the culture, it can be really valuable, because it's sort of like it's okay to break things as long as we can fix them really quickly, and as long as like we catch them before they get rolled out. And another thing that I think is really interesting here is being able to go from a decision that you made in production. Can you track, or not a decision that you made, a decision that a model made in production, can you track back exactly which model created that, and how that model was built, and what data it was trained on, and maybe how it performed in Lime, and things like this. So being able to track the lineage of the model development back down to these sort of individual parameter tweakings is important for continuous delivery. And then observability, like once the model's in production, it would be really nice if we could track the model health with the same metrics that we use in development. And this way we can see the drift of the model versus how it was performing in development versus how it's performing in production. And if the model health drops below a certain threshold, we should page a human. So, I mean, I've talked about this big vision then for like how we can apply everything we've learned from DevOps to data science. And the natural question is, well, okay, where to start? And where we have started on our journey here is to think about how to solve the version control problem and the development workflow and collaboration problem. because, like I said, everything else is built on top of that. Until we have those fundamentals in place and really strong, it's going to be hard to do all the other sort of fancy stuff on top. So like I said, data science and AI is harder than software engineering because it has more moving parts. There's all these different types of data, runtime environments, models, notebooks, and the data, the model, like I said, is an artifact of the code plus the data. And so I'm going to humbly propose a solution for your consideration. If you want to do reproducible data science and AI and machine learning, then you need to track at least these three things. You need to track the environment. So you need to track exactly which operating system image you used and exactly which versions of the libraries you used, because there might be bugs in different versions of the libraries. You need to track everything about your code in the notebooks, including their parameters. And you need to track your data, and your data needs to be versioned. So with these three things, you have a chance of achieving reproducibility. And once you have reproducibility, you have all the benefits that I talked about in terms of it's easier for someone who's testing or doing QA on the model to get back to the same place as you. So how? Well, as I promised, there are some open source tools that can help. And I see a Docker t-shirt down here, so that's great. In the DevOps world, Docker has been a big hit. Who's heard of Docker? OK, cool. So Docker helps you pin down the exact execution environment that your model training is happening in. It's a very popular open source project. And a Docker container is like a tiny, frozen, runnable copy of your computer's file system. I mean, most of you here know what it is, so I'll go quickly on this bit. You can determine the exact version of all the dependencies and exactly how your data science code, exactly the version it was running. And then you can build, ship, and run this thing and move it around between your laptop or a cluster or the cloud where it's running in production. And so you can write these things called Docker files that declare exactly what versions of things you want. And then you can build, this should be the other way around, you can build a Docker image from a Docker file and then push it to a Docker registry. So that's fine. We should run, basically I think what we're saying here is that every time we do some data science, we should do it inside a Docker container, and we should record exactly which version of the container was used, or the container image, so that later, when we need to come back to it, we can get back exactly to that state. And it's especially important if you think about, like, I want to be able to go back to this in a year, and then, yeah, the version of Keras I'm using, the version of TensorFlow I'm using will have moved on by then, but I still want to be able to go and see exactly how that model was created on those old versions of the software, so it's useful. So for pinning down code in notebooks, Git is very popular for developers, but it has some problems in data science. It's not natural to commit every time you change anything, like while you're tuning parameters. And you generate these important results while you're iterating on your notebook. Git doesn't cope well with large files, but data scientists often mingle their code and their data. And diffing and merging Jupyter notebooks, like I said, is not easy. So I'm proposing a new version control and collaboration system for AI. It uses an open source project that we've developed called .mesh, which is powered by a file system called ZFS. Has anyone here heard of ZFS? A few people? OK, cool. We built on top of this file system, which I don't have time to go into, but it basically gives you this thing that's like Git for data, and it can handle large data sets efficiently and deal with like terabytes of data files in your workspace. And the other thing we heard was that it's really important to be able to track the relationship between your statistics and your parameters, and also your lineage and your provenance. So I'll give a very short demo. And then ask for your help. So I'll be really quick. I have here hopefully you can see. I'll make it a bit bigger. So I have here a data wrangling notebook. Oh, that's pretty big. Hopefully everyone can see that. So the data wrangling notebook is going to combine house price data from two estate agents. And if I just click Run All Cells, it's going to read them in from two CSV files and output them into another CSV file. And then So in this environment that we've got set up here, every time I click save, and there's like some new parameters and summary stats, the system makes a new version. So this commit records lots of metadata, more metadata than you get out of Git. It records the exact versions of the input data that we used, and so on. And the CPUs that you had on your runner, and all these things. And so you can see over here, there's this provenance graph has shown up. And so this provenance graph says, well, we used, I can show you the exact versions, this version of Agent 1 and this version of Agent 2 were combined by this version of this code and created this version of this data. And so that's pretty useful for data wrangling. And the next thing is, if we actually do some data science, I'm not the best data scientist in the world, but I do have this simple linear regression model that then tries to predict the house prices based on some features of the data. And so you can see we've got some correlation between the square footage and the number of bedrooms and bathrooms. I know this is quite a boring example. Everyone does house price data. But the point is, we pick our features here, square footage, and then we say, well, what error rate does that give us? It's some huge honking great error rate. And as soon as I hit save, then I'm tracking that fact. So, well, hopefully in a second. So I'm tracking the fact that there was this run of this version of the notebook that generated this error rate. And I can see it here. So I can see, like 14 seconds ago, some guy called Luke did a run and used the square footage to generate an error rate here. And I can go into this specific thing, and I can say, well, it was this exact version of the notebook that was used to create that thing. And it used this exact version of the input data, and so on. And so very quickly, I'll do a little bit more data science. I'm going to add another feature to the model. I'm just going to click run a few times and hit save. And now I can compare these two runs. And this gets even more useful when you have multiple data scientists collaborating together. So you can say, like, Alice got a better error rate than Bob, and like, let's go and look at which features she used, and so on. And so you can sort of compare them in this graph, and you can see, there we go. You can see that my error rate got very slightly better when I added the bedrooms as well as the features. So this is what we're working on. The last thing I wanted to say was that I need your help. So we're a little startup. We're trying to figure out whether this stuff that we're working on is useful. So please, 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 just get your phone out and drop me an email if this stuff is interesting to you, because I'd love to talk to more people about the problem space and see if we can build something useful. So thank you. I think I've got 5 minutes for questions.